We will continue with the point processes, and the next operation that we will see is this increased graph. So just a reminder of kind of operations. Okay, so we have an image, we have an output image. And the kind of operations we are studying now are those for which one pixel is transformed into another pixel. So J and R is a transformation of the equality at the same location. And the one that we will see today, this one. So we are starting with the gamma transformation. So the gamma transformation, okay, if there is no ambiguity, there is no need to put the argument. Okay, if there is an ambiguity, then you need. But if there is no ambiguity, then I have only says this one is pi, then I divided by pi, 1 divided by gamma. And this has the same structure that transformation we were seeing the other day. The other day we will see right. Pi and J. Then stay. This is J. This is I. And then I. So why I'm saying that this has the same structure. Okay, so we were saying the other day, this part is moving the coordinate axis. So let's call this operation. Let's call this operation an operation F. Okay, good. Then we apply another transformation that we need. And then we are applying how this is F minus 1. Actually, the F minus 1 if we want. Yeah, let's keep it this way. There are several ways of rearranging this, but let's keep it this way. And this has the same structure. So this is F. And this is F minus 1. And this one is A. So there are many transformations that has this form. So they have this form. So J is F minus 1 applied to, then this is applied to F, then this is applied to I. Have to close parentheses. Okay, so you start with something, you apply a transformation. So this is just kind of axis correction or whatever. Then you apply a transformation, and then you undo the original transformation. So this one was shifted. This one is a scaling. So my numbers, my input images are between 0 and 255. Say. So first I divide by 255. Then now my new image is between 0 and 1. Then I apply a transformation, and then I bring it back to 0 to 55. That's it. And if you want, you can also write this. I will not use forms anymore. You can use write this at n minus 1, apply it, apply it, n, and then this is how I apply. And then if you want, you can say J of R is F minus 1 applied to B, applied to F, applied to y, and this is applied to y. Both ways are correct ways of writing that. So here we are emphasizing that I is a function. Here we are emphasizing that this F applies to I. So I is more like an object, like a matrix here. Here I is kind of matrix, J is a kind of matrix. Here we are emphasizing that I is a function of I. Okay, so here we are. So this is our transformation for gamma larger than 1. This has this shape. So this is identity transformation, so no transformation at all. And for gamma, I don't know which value, let's say 2. So we have this or 1.2 or 1.3 or whatever we have. So it goes away this direction. And this is the histogram, this is the transformation. Now we will make this question. So are we increasing or decreasing the contrast? What do you think? Of those things, we are increasing the contrast. Right? Who thinks we are decreasing the contrast? 3, 4. Actually, we are doing both. So remind that the contrast is related to the slope. So here the slope is greater than 1. So we are increasing the contrast here. This for this input gray values or input color values. And here the slope is smaller than 1. And then we are decreasing the contrast here. So here we are decreasing, here we are increasing. We are doing both same time, but in different ranges of the input values. So for the low input values, we are increasing. For the high input values, we are decreasing. Okay, so now gamma is smaller than 1. If gamma is smaller than 1, now the curve bends in the other direction. And again, we have the same behavior. So for the low values, we are decreasing the contrast. For the high values, we are increasing the contrast. And actually, this is very much seen here. Upper part of the temple. So we see that now the windows are, the doors are very much are better seen. Here they were seen. And here it is the same. This part that was dark, with this gamma, we can see it better. And with this gamma, we can see it. Okay, and then we can study what is the effect on the histogram. So this is the original histogram, and this is with gamma equal 2, with gamma equal 1/2. And we recognize a couple of patterns that we already know. So we have poles and we have spikes. Okay, so where are the spikes and the holes coming from? Do you remember? So this is related to increasing or decreasing the contrast. So let's take one. So here we will have a to the image I, here we will have 2i, and here we will have 1/2. We have two transformations there. And we have the value 0, 1. So 2i. So 2i is 0 goes to 0, 1 goes to 2, 2 plus 4, 3, and so on. The half of I is 0 goes to 0, 1 let's say that we round down. So 1 goes to 0, this goes to 1, 1. So what about 1? 1 is missing. So if you have an input image, and when you increase the contrast, there are holes in the histogram. So there are no value in the output that takes value 1. There is no pixel in the output that takes value 1. So these are creating holes. And what about this one? There are 2 values that collapse into the same one. And this collapsing is making spikes. These 2 together, they are making spikes. So here in this particular transformation, they should all have more or less the same kind of spikes. But let's say that instead of a half, what we have is a value of 1.9. So for some of the values that will be spiked, for some others that will not be. Sorry, this is not 3.9. So it has to be smaller than 1. So 0.9. Okay, so for some of the values that will be spiked, for some others that will not be. So these spikes are where we are decreasing the contrast. These poles are where we are increasing the contrast. Same here. Spikes, these are the poles. And we understand where they're coming. Any question? Okay, this is a reminder of what the PDF is. So these are reminders, so they are the same slides as the ones we had before. And this is an example, so we have seen this is the probability density function. So if we say probability density function is because we have divided by the total number of pixels. So this is not a histogram anymore, but it is a normalized histogram if you want. And the CDF, the cumulative density function, is the addition up to a particular point, the CDF. So you can just remind us. The CDF value G is the probability of the image taking a value that is smaller for equal G. This is the sum of G prime 0 E or CDF or PDF or. And there is an interesting instruction here that is why I wrote it. That is, this argument has to be different from this one. This one is the same. But if you want to jump and to use the same variable, you have to use a different one. This is called a dummy variable. So it is an auxiliary variable that you use to sum. Dummy goes there, and this G is just to stop the sum. So we keep adding G primes from 0 up to G, and G is the stopper. So this happens very often. So the equivalent with integrals is fine. Probably you have seen this kind of expressions. And in this kind of expression. But this is the totally same equivalent as this one. So this one is a dummy variable that used to integrate. It's a dummy variable that used to sum. Okay, so yeah, then we now I will use a different notation. Okay? I will use a different notation. So look at this CDF. So you can call it CDF or PDF in capital letters in these slides. I will keep calling it CDF. Okay, so the CDF goes from 0 to 1. Okay, and so this is the range, and the domain is 0 to 55. So I can use it as a transformation. So I will construct a new image. I will construct a new image. J, that is CDF, right? Y. But the CDF goes from 0 to 1. So I will multiply by 55, having back to 0 to 55. So this value is between 0 and 55. So let's put numbers here. This goes from 0. This one goes 0 to 1. This one goes again 0 to 55. So I have constructed the new image in this way. And this operation here. So this operation here is called histogram equalization. Let's see what. Okay, so let's explain why it is called first histogram equalization. So let's say, because it is not explained in the slides. Okay, so let's say that the histogram of I, and this is the EDF. Right here, all that. Okay, so the difference is this is the random variable, this is a particular value of that random variable. So a small I is a particular value, the capital I is the random variable. So let's say that the PDF is like this. It is like this. It is unique. All values have the same probability. What is the probability, by the way? It is uniform. One part of people arrive. So they are all equally likely. Actually, this goes from 0 to 255. So to be again absolutely correct, this is 1/256, but we have to include the 0. And remind that this is just a representation, but they are discrete deltas. That I don't want to write gross or make, but they are discrete. Okay, so now, what is the integral of this? What is this cumulative sum? The cumulative sum. I, now this is the CDF I, and it is this sum, but this sum is this one. With this identity transformation. So if my input is uniform, my CDF will be a RAM, will be identity. And then there is no transformation. So this is a transformation that uniformity is go unchanged. Okay. And J will not completely succeed, but it will try to make I more uniform. So it will try to transform I into this. It will not completely succeed. And the reason is that because not all the values are equally likely, there will be jumps, and these jumps make the output not to be exactly uniform. Okay, so let's see the effect. Let's see the effect. So now we will use this one as transformation. we have to scale it back to 0 to 55, but that's fine. Okay, so let's say that we have this value image. The value, we know what it is. It is the average of the red, green, and blue channels. And this is the histogram of that. This is the CDF. And this is the effect of transforming this according to this transformation. And I think there is the output. So this is the CDF. We have transformed it by multiplying by between 0 and 255. We have transformed it into a lookup table. And this is, if you see this value, have to substitute by this one. And then we see something. Some of the values, they are compressed here, while some others are rather expanded. So why is that? And let's look at the original histogram. So the original histogram, most of the values of this image are between 0, 1, 50 and 100. And in the region of 200s, there are very few values. So this is a kind of inefficient use of the dynamic range. So this is our dynamic range. These are the values that we can take. And it is rather inefficient because some of them, they are somehow very much used, but some others, they are very little used. So why not try to make them, all of them, equally used? And this is this CDF. Actually, that is what it is doing. So the values that are, there are many values of them. So you see 50 is transformed into 25. 100 is transformed into 150. So before we only had 50 values here, but now we have 125 values there. And we are spreading all these pixels. We are spreading all those pixels. So 50 values, we are spreading into 125 values. So they will be less used. So we will try to make this down. And what about these ones? These ones, let's say from 150 to 200s, they are transformed into 210 and 220. So 50 values here, they are transformed into 10. So now they will compress. And the overall effect is that more or less they will be more or less equally used. Okay, so let's see the output. The output histogram. This was the input, this is the output, and we see that there are some values that there are holes, there are places where we are not using those values. And here it is relatively uniform, but this uniform is not the same as this one. So we don't totally succeed, but certainly it is much better than it was before. Before, none of these values were used. Now they are used. This region that was very crowded, we have expanded. Because of the expansion, we are creating holes. And then these values, again, they are compressed and using more. Look at this one and this one. They're not exactly the same height, but they're much more uniform than they used to be before. So this one was 0, this one had something. Now they are, okay, not exactly the same value, but more similar. Okay, so this transformation is called histogram equalization. Any question of this one? No? Okay, so yeah, so this was the luminance image. So before we did it with the value, now with the luminance, we can do it again. So it is the same process. So you compute the CDF, and then you multiply by 255, and then you apply. Okay, this is what we get. And here we get the two. So luminance and equalized luminance image. For the equalized luminance image, we are exploiting better the dynamic range, but the appearance is a little bit artificial, I think. So this is not a natural lighting. So natural lighting is not uniform. Okay, so for the computer, it lights because all the values are equally likely, but from the human perception point of view, we don't like it so much. It is a little bit unnatural. Okay, but you have better contrast here. Let's see. The distance between minimum and maximum is larger there. Okay, so we can do the same with colors. So you have a color image, and then you compute the 3 histograms, and now you compute the 3 CDFs, and you convert them into lookup tables, and then you can equalize the 3 channels independently, and this is the result. And now even the colors, they are a little bit unnatural. Okay, so yeah, we have a comparison of the two. Okay, but we can do something else. That is, okay, so before each channel was processed with its own CDF. What if I take, these are the color CDFs. Now, what if I take the luminance update? I use the CDF from the luminance, and I apply the 3 channels. And this is the result. So I don't mean that this is better, okay, but now at least the relative colors, they are not, so they are distorted in a different way. Here we have. So depending on what is your purpose and what is the kind of images that you have, what is important here is that you can use independent CDFs for each one of the channels, like this one, or you can use the same CDF for all channels. You can do very creative and take the CDF from the luminance, the CDF of the value, the CDF of whatever. Yeah, so here we have a different comparison of the different configurations. So this was the original, this is the luminance equalized. The luminance equalized. The background is highly increased. But for instance, here it's saturated. It depends on what you want to highlight. You may want one transformation or the other. Any question? Okay, so let's continue with another operation. It's somehow similar to this one. That is histogram matching. So let me go to the end. So the white on that. And then we'll come back to how this is done. So I think this is a good example. So let's say that you have 2 pictures of the same garden. This is one of the pictures, this is the other picture. Actually, the garden looks like this. These are all natural photos. And how these ones have been saturated. So the camera was badly calibrated here. Then your colors are saturated. So they shouldn't look like this. They should look like this. Okay, so now you have 2 images, I and J, and you want the histogram of I to be as similar as possible to the histogram of J. Okay, so now we have 2 images. Or we call it I and I. Okay. I and image I it's your reference. And you have 2 CDFs. So you have the CDF of I, have the CDF, then I reference. And what do you want is to sometimes If there is no doubt, you can skip the argument. If there is doubt, and here I think that could be doubt. So the argument of the CDF is a gray value, it's not a location. Here it is a location. The argument of an image is a location. The argument of a CDF is a gray value. Okay, so now what I want is to construct a new image that we call it J. And I want to construct an image in such a way that the CDF of J is similar somehow to the CDF of I. This is my goal. And I want that because one of my cameras, the colors were degrading. Here we have an example, here is another example. And this will be the result. So let's see, this was the degraded image, and this is now with the same CDF. Now the colors are natural. And you can have the same couple of cameras, but they have been calibrated in different ways. So you know that the two should have the same colors, but they are not. But you can somehow make one look like the other. So this is why we want to do this. Okay, so let's see how to do this. Now we come back. Okay, so yeah, I have called it I and I red, and please call it I and J. Okay, so J is our reference. Okay, so let's look at the two CDFs. So I have the CDF of I have the CDF of my reference. And I have to make the following transformation. So I have to find, so because these are CDFs, they go from 0 to 1. And just for simplicity, we have taken here just 15 values. Okay, so our images are 4 bits. So they go from 0 to 15. And then I want to transform the input value 5. So in my left image, I have a value 5. What should be the output? Okay, so I will do the following. So I will look for, so what is the probability of being smaller than 5, smaller or equal to 5? So in image I, that is 0.65, let's say. So now I have to do in image J for a value such that the probability of being smaller than that value is also around 0.65. Okay. If I can find 0.65 exactly, the better. Let's say that this is exactly the same. So now 5 should be equal to 30%. And in practice, it will never be exactly the value you are looking for. So we have to put a constraint. So the constraint is that the 0.65 has to be in the middle between the value that you want to substitute and the previous value. So 0.65 is between these two values. This is value J, Tj, the value Tj. This is the value J minus 1, J minus 1. So 0.65 has to be between. Okay, so I will substitute value Tj. This is my transformation. How do we write things in this way? I will come back to my notation where I have I ref and I. So you start with a value. So you start with a value I at a given location. This is your 5. Okay, so then numbers. It's 5. Now I compute CDF of this one. So this one is 0.65. And now look at the slide again. So we started with 5. go to 0.65. And now I start from the 0.65 here, and I look for the value such that J also, so this value is the smallest one, such that the probability of being larger than that, than 10, is it's always larger than 0.65. So I will call that an operation. We call that operation. This is with image I. I will call that operation here I minus 1. But this is the one that takes the 0.65 and looks for the 10. So now this thing is 10. And this will be my output value. Will be my output. So you start with the value. You look how many pixel values are smaller than that. And then you look into the other item, which is a value that has more or less the same probability. Okay, so this operation here, it's called histogram matching. We are matching the histogram of an input image I, the histogram of a reference image. So actually, histogram equalization is a particular case of this one. This one is a uniform distribution. And then we again understand, okay, we will not totally succeed in making it, the two histograms to be completely the same, because we didn't succeed with the uniform, the histogram equalization, make it completely flat. But they will be more similar, and they're sufficiently similar. So they are sufficiently similar. Probably the histogram of this, it's not exactly the same the histogram of this, but they're sufficiently similar so as to make the two images similar enough. Same here. So the histogram of this will not be exactly the same the histogram of this. They're similar enough. Any question? Okay, so let's make a break. No, we go down. Yeah. Okay, so what is left here? So there are different so this was the concept, and then the rest is just ideas around the same concept. The concept now, I'm really absolute. What could be a MATLAB component that MATLAB, and then as an example, so let's say that we have the 16 values only, have the 16 values, and then we compute the CDF, and then we take another with 60 values that has this CDF. So we compute the CDF, and we construct our table. So this is the same concept that we have explained. We have the image CDF, we have the target CDF, and then this gives us a lookup table. So lookup table is when you see value for the input image, you should substitute by value 10. And this is so because the probability of being a smaller or equal to 1 is approximately the same as the probability of being smaller or equal to 10. Or this, and this is the result. So this is the input, this is the target, this is the lookup table, and this is what we get. So we don't get exactly the same that we wanted. You see that this is growing smoothly, this is growing These jumps are caused by this big jump here. There is a huge probability change from 0.1 to 0.4. And this creates several values to be mapping the same. And so we don't completely succeed, but it is more similar, and we have seen this sufficiently similar. Okay, so we have this one that was a relatively dark image. We have this one that is relatively bright. And then if we refine, so if we compute this histogram matching, then we can make this one brighter. For instance, something interesting is this table here. This table here was in the original image. We haven't invented anything. It was there, but there was very little contrast. So let's see. By increasing the contrast, we can see details were present in the original image, but we could not see. Okay, so we can do the same with all of images. So we have different PDFs for the different channels, for the luminance. And then we can have the CDF, one of them. And we can have the color image, another color image with different PDFs, different CDFs. And then we can do this. We can do the following. So we can use the luminosity CDF. So there is a lookup table associated with this CDF. Then one of luminance. Okay, the other ones, the other three, okay, the other three, okay. And you use the luminance of that. So only the luminance. Transform all the color bands here. This is what. So you don't completely succeed in making the two luminances the same, but they're sufficiently close. The luminance of this is close to the luminance of this. And the colors, they are not perfect colors, but they are not so natural. Okay, so this is different. So this just the original CDF of the luminance, the original CDF of the other image. And then this is the lookup table. So this is the transformation between these two. This is this preparation that we have here. You take an input value, and then you are producing an output. You are going from 5 to 10. Okay, so this is from 5 to 10. This is this transformation here. And then this is the final luminance, the one after transformation. After transforming, you have this one. But it is not exactly the same as the target, but it is close enough. Then you can look at the different PDFs, how they have changed. These were the original histograms, these are the final histograms. Some places we have increased the contrast, in some other places we have increased the contrast. You know, now these things. Different CDFs, 4 of them. You know, you can do the same with this unnatural mapping that we have with the histogram equalization. So now, let's say that my lookup table, so we have seen two possibilities. One is to use the CDF of each one of the bands, independently. We got this one, and to use the CDF of the luminance, we got this one. You see, they're not the same. I would say these colors are a bit more natural than this one. And now we can do histogram matching. So histogram matching is, okay, I want the CDF of the bands be similar to the CDF of the luminance. You recognize this structure that we have. So take the CDF of the bands and to try to match them to the CDF of the luminance. And now the colors are different. We have to try and create some kind of it is not equalization, so it's not more uniform. It is at least all the bands have something similar to the unions. Now transformation looks more natural. So this is again looking at all the possible functions involved. So the concepts are the same. And you can do these things. This one, again, all possible PDF, CDF, that they should. And this is what we can do. So you have in this example here, what we have done is red, we have matched red, green to green. You could match the luminances, you could match whatever. In this particular case, we have matched the values. Any question? Entertainment. So next lecture is about color perception. So how do we see colors? Okay, so probably you are familiar with this kind of representation where we have three channels. We have already introduced them. Red, green, and blue. We have said that any color is a combination of a different value between red, green, and blue. And for instance, if you put the same value to the red and green channel and 0 to blue, what you get is yellow. So for instance, let's say that I put 255 in red, 255 in yellow, 0 in blue. Then what I have is a very intense the same between green and blue. So what you get is cyan, magenta. And then if you don't put the same number, so if any one of them, so for getting yellow, you need two values of the same value. The equation is simple. So we have said that magenta is red and blue. So I want the two red and blue values to have the same value. Red, 0. And so this kind of structures, this is magenta. And depending on X, so for X equals 0, line. For X equal to 55, have a very, very intense magenta. And then for X in between, what you get is a degradation between. So this is a technology that was used to display digital images. Doesn't mean that all technologies are like this, but this illustrates very well how things work. So let's say that if you want to show this image here, this kind of the person. So you want to show this, but in reality, what you do is you have three superposed grids of vision. So you will have layers. So the layers is a diode. So these diodes either emit in red or in green or in blue. That is all they can do. And we have the three layers, they are intermixed. And so physically, they are very close to each other. So that this is kind of exaggeration of how but they are the three are intermixed. Then what we have to you have transferred the problem of showing colors to controlling intensities. How do you understand? Okay, this is a diode. A diode, depending on the input voltage or input current, it will emit more or less. So depending on what is my intensity in the machine, we have no emission. So no emission is okay. But no voltage are emitted by this case. Or I have very intense rate. I am emitting a lot of voltage. And then what I have to control is this intensity. So this number 0 to 55 is controlling is how many photons you are emitting from this lens. This technology was a CRT, a cathode ray tube for liquid crystal displays. There are several technologies, and they are all more or less going into the same direction. So they have just three types of devices that can emit a single wavelength. What you are controlling is the intensity of that wave, that emission. And then you can be very creative how you organize these layers in space. You can imagine that depending on how you organize them, can be more or less efficient in energy. So, so you don't need to emit as many photons to have the same kind of quality, image quality as with some other technologies. So I don't know which one is more efficient, but see that the quality is reasons here. This is clearly this has to be the less quality, but there are many areas that are not emitting. There are a lot of black areas. This one. Okay, and the same when you print. So when you print, you look pretty closely to the image that is in, for instance, in the metro advertisements and symbols. You get very close to it. What you see is that instead of printing in red, green, and blue, they print in magenta, cyan, and yellow. These are not colors by chance. So now you understand why these colors. These are these colors. The colors of this ball. So 0x, x0x, xx0, and the other last one is 0x. So they use this kind of combination. And black. Black is xxx. So it's a gray one. Okay, and now they use the same kind of trick. So they will print in 3 different grids, actually 4 different grids, but you only need 3. So they are superposed, and then this superposition they create this pattern. So if you get pretty close to the advertisement, you will see the printing pattern. So it is kind of similar to what we do with displays. And then it is the same concept. Decompose your original image in 3 channels. But now the 3 channels are cyan, magenta, and yellow. You can add a 4th one. The reason for the 4th one is price. So these 3 channels, they are more expensive than this one. So you need only 3 to have a full basis of the color space. We will explore these concepts later. Not today, but next day. And so you only need 3, but if you use these 3, they are more expensive. Black ink is very cheap. And try to support one. Then try to put as much as you can in this one, whatever you can distribute in the other thing. And then these are the densities, and then you have to print them following different grids. So this is how you are printing. And then the superposition of these 4. If you look from the distance, you don't see the pattern anymore. Okay, so how do we perceive colors? So let's start with the eye. So the eye, light is coming from here, and our sensors are here. So the sensors like this. So you have a first layer of cells. This first layer of cells. So the light goes in. So they are partly transparent. They absorb a little bit of light, but still light can go through. And then there's a layer of some other cells that will see the the light and transform it into electric pulse. And we have 4 different kinds of cells. These ones are rods. These are cones. And we have 3 different kinds of cones. We have red cone, blue cone, and green cone. And then these cells, so these cells here, are both are there, are in the retina. So this back part of the eye is called the retina. That is the retina. And in the retina, we have an area that is called the fovea, that where we have more receptors. See, there is another region, that is this one, that we don't have any receptor at all. So where the optic nerve reaches the eye, here we don't have a receptor. So we have a blind spot there. And okay, so have this light coming in, and then it goes to the cells, and the cells transform light into chemical signal, and this chemical signal into an electric signal. And actually, there's a protein that does that. It is not mentioned here in the slides, but if you're interested, it is called the rhodopsin. So the rhodopsin is the protein that receives the photons as a chemical chain. And then this chemical chain opens pores in the cell, and then form ions and being and so on. So that is a beautiful cascade of events. Okay, so the retina. So the retina looks like this. So this is, you see that the density of cells is different in space. So there is a region where we have more cells, and as you go away from that region, the cells are sparse and sparse. So these are cones and rods. So this region where cells are more packed, this is the fovea. So this fovea here is a region where cells are very tight with each other. And then we can measure what is the density of rods and cones as we go away from the fovea. So this is you go away from the fovea. So this is the fovea. This is an angle, and then this angle goes towards the node. So we go away from the node. And here is the optic disc. So here we are blind. We don't have any receptor there. And then we see that photons, they try to concentrate at the fovea. Doesn't mean that we don't have any cone away, but most of them are in the fovea. This fovea is just minus 10 degrees. And then the rods is the opposite. So at the fovea, we have very few rods. But as you go away from the fovea, now you have a lot of rods. So something interesting, bones are sensitive to colors. Rods are not. So rods are sensitive to photons. They don't care about which colors of the photons are. And then you can see the difference between. So these are much more sensitive than the cones to photons. Okay, so rods with very few photons, they spike a lot. The cones are not like that. So the rods are the ones responsible for our night vision. By night, the colors. Why? If there are very few photons, the few photons that are received, they are not excited enough the cones, but they are excited the rods. So by night, you don't see colors. And by day, you see the colors. Yeah, the rods are also responding, but the bones are able to discriminate. Okay, so yeah, this is how they look at it. So rods are finer. We have a lot of rods, and then from time to time have a road. In the phobia, it is the opposite. Have a lot of bones, but they're very fine. Then you have the let's see, go away, you have a little bit its situation. Okay, so that means that we are maximally sensitive. We are maximally sensitive is minus 10 degrees. So that is a very narrow cone protomass. So actually, when you look at an image, this is what you see. This you have a region where your phobia is moving. You have a region where you have a lot of things. Then as you go away from the phobia, you don't see the things anymore because you don't have sensors for that. So you don't have sensors. Then you look like you see like that. But then what you do is you move your phobia. Now the phobia is moving to a different place, and now to a different place, and now to a different place, and now to a different place. And you do this very often, very quickly. This is called the saccade. And then your brain is the one that is integrating all this. But there is a tiny integration. So that because we are really fast doing this. You don't realize that your phobia and your eyes doing this. But your brain is the one taking all these things and you sum them somehow in a clever way. Now you have very good detail all over the place. So this is very, very interesting process that we have. The other one is that how can I simulate this process having more detail in one location and then a smaller detail as you go away. And this is done through this log polar transform. So the log polar transform is a mathematical way of simulating this process of having more detail in some regional analysis. And here we have this. Okay, so I will transform my image into a different one. This is the luminance image of the output image that we will see. And I will define this output in a polar space. This one is in Cartesian domain. So you start with so this point. I want to look at this point, rho phi. At this rho phi, I have to translate rho and phi into x and y. And instead of going from rho to x and y, we will go the other direction. But if you solve for x and y, then you have this like coordinates. This is coordinates. It's something that you know. You don't know the log polar, but you know the polar. So polar x, y, have a point here. And you know how to calculate r and phi there. Calculate r at square root of the square root of phi. Phi is the r tangent is y divided by x. And if you want to go in the other direction, then x is r cosine phi, y is r sine. So now you can think of things as a transformation that takes x and y, that is a point, and transforms, I will call it E, a polar transform. the polar transform. R5. This is RP. This is the location in Cartesian coordinates. You apply some transformation and then you have the polar coordinates. And you have the option. Is polar -1, that is the inverse of this function, obviously to 1. And then this is applied. And when something is a vector, you have to say it. When something is a scalar, you have to say it. All these are scalars. These are vectors. So remind my saying that you have to speak the language. Okay? The language of this one have to speak it correctly. The language of vector have also to speak it correctly. Then apply mathematics. Okay, so yeah, so either you give P or you give P -1. So in this case, it is simpler to write P minus. So given X and Y, how to calculate rho and phi. And this is done in this way. So you give me X and Y, and you give me the point you're looking at. So this is where the phobia is looking. So I will compute R, and from R, I will compute, make this transformation. So you see all these are parameters. So M, alpha, and beta are parameters. So they are numbers that I need. And these are real numbers that are positive. And there is a constraint. Beta has to be larger than this. So you can take any beta as long as it fulfills this constraint. So you give me X and Y, then I compute R. With R, I can compute rho. And then with X and Y, I can also compute this R tangent. So this is the same as in the polar transform. So the log polar is because this radius here is calculated. It is almost like the polar transform. So without the logarithm and alpha, beta, n would be just the polar transform. But then you have n, alpha, and beta, the logarithm. It's not the polar, it is the log. The concept is the same as in the polar transform. So you give me a point. You give me a point. X and Y, and I can compute R and phi. Or you give me R and phi, and I can compute X and Y. So now we know how to compare coordinates. So now what we will have is an image. I can take this one. Let's do it with polar, okay? So let's do it. Polar is equal to rho. So I can construct here my R by axis. And then I can say the image at this point, indeed, at this R phi is the same value that is coming from that is I. This is what this equation say. So the image at this point has the same value as the input image, the Cartesian one, but that's but we have made a change of axis. So let's take the easy axis, just an easy one. So let's say that our color image is like this. Let's make it simple. This and this. Okay, so this part is black. Part is black. And this part has 4 colors. This one, and it has our leaves. Okay, now I will make my and 5. Okay, so 5 goes from 0 to 360. And R, say that my maximum access here is 1. So that was last second. Okay, so I have that. It's 1. I could have that here. Radii. Okay, so my image is this. Okay, it's a color list. Before I have this black. So all this region is black. Okay, now beyond 1 it is also black. Now between 0 and 9 it is green. 90. This is green. This is green. Between 90 and 108 it's red. 80. And from 180 to the end, it's red. So this is my polar transform image of this one. So what's my log polar? So log polar makes that this axis is logarithmic. Log polar, this axis is logarithmic. But aside from that, there is no other thing. Okay, good. So this is how my log polar image looks like. So you take this image, this is the log polar representation of that. Same I have made with the C2, but now with a key. And so this is log polar. You want to come back to the Cartesian domain. Now this is compressed. So you have fewer samples in the outer part because of the log, because of the logarithm. Then you have fewer details in here. So this is the Cartesian representation. So you go from Cartesian to log polar, you sample, then you come back to Cartesian. This was a video. So, but in the PDF you cannot see something. But in this video, the fovea was moving, and then you can see that the details away from the fovea, you have less details. Okay. Another interesting feature of our visual system is that let's say that this cell, excites, so it receives a lot of photons and it then starts spiking. So the connection between these cells is such that the nearby cell is inhibited. So this is a feature of our visual system. So if a cell excites, the nearby cells are inhibited. So that means that once a cell is excited, the nearby will be inhibited, and that means that we will only see edges. So we don't see the values in between. So actually, we have this fovea effect, and on top of that, the fovea, the response that our eye is giving, is just the edges. So the brain is just receiving the edges. It sees the colors at the edges. Okay, so the color at the edge, they are seen. And then we have to interpolate the colors in between. So the brain has to interpolate the colors in between. And we have on top of that, we have the fovea. Okay, so. Okay, then we can try to make an experiment how many cones we have of each kind. Okay, so let's do the following. Let's say that I have an image. Say that we have an image. So for every value, for every pixel here, we have a red, green, and blue value. So let's concentrate in the red. Okay. So we have 4 times 4 red pixels. And now I'll do the following. So I will take these 4 values, compute the average, and I will have a single one. So I have only one value there. And I do the same everywhere. So now my new image only has 2 times 2 values. So I have fewer values. They are bigger, but I have less contrast. In the 4 times 4, I could have more details, no? Because I can put different numbers. Now in the 2 by 2, I can only put 4 numbers. Before I could put 16 different numbers. Okay, so let's take this image. This image has, I don't know how large this is. Let's say it is 1,000 times 1,000. So we have 1,000,000 different numbers for each one of the channels. So we have 1,000,000 red, 1,000,000 blue, 1,000,000 green. So now we do this process. Okay, in this process of averaging neighbor pixels, now we have 1/4 of the values. Because we are dividing by 2 in one direction, dividing the 2 in the other direction, so we have 1/4 of the values. And okay, so this had 1,000 times 1,000. This has 500 times 500, and you barely see the difference. They look very similar. Okay, now you do it 4 times. Okay, now I start to so now your pixels are 4 times 4 instead of 2 times 2. So now you have 16 times less information, and then you see the difference. And with 8, so now you have 8 pixels and 8 pixels. So it is the same process here. Same process, but instead of 2 times 2, it is 8 times 8. You see the difference, and with 16, you see even more. Okay, this makes sense. So our resolution is not high enough to recognize this one. So they look very similar, but this one we already see. Okay, so now I will do the same now with the different bands. Okay, so you can imagine this pixelization is terrible. Okay, so we have such a big squares that we see that we have very poor quality. We don't have enough numbers to recognize. We will do that transformation. So 16 times 16 to the red, to the green, and to the blue channel. And yeah, we see differences. Okay, it is not like the original, but this image is not so bad. This image is not so bad. This is terrible. So that means that we are not so sensitive to red and blue. So we have many more green cones than red and blue cones. Many more. Actually, this is consistent, I think, with one of the pictures before. When we look at this, most of the points, most of the cones are red, are green. And now we have more red and very few blues. You may remember, do you remember the luminance transformation that we did in one of the first lectures? So the luminance, computed, I'm putting approximate numbers, okay? So it was something like 0.6 green, plus 0.3 red, plus 0.1 blue, something like that. And now we understand these numbers. We have many more green cones than red cones, and blue cones, and they're more red than blue. So we should give more weight to green, and then to red, and then to blue, because we are not so sensitive to blue. So then we here. Okay, so yeah, this is the inhibition that I told you. But how to model that mathematically? So a way to model that. So let's say that I have this image, here, this image, and I want to simulate the process of inhibition. When you want to simulate the process of inhibition, you can try to do that some way. The way that is useful is by convolving with this function. So this function somehow, if a cell is activated, the nearby cells are deactivated. Okay, so this is just this function here is called the Laplacian of the Gaussian. So the Laplacian of the Gaussian is the second derivative of the Gaussian. So you take the Gaussian, compute the second derivative with respect to R. This is what you get. And this function is different. And this is in one dimension, this is in two dimensions. So all the nearby cells get activity. And then we will convolve with this, and this has a frequency response. A frequency response makes the Fourier transform. This is what we get. How would you describe that kind of thing? It's low pass, high pass, band pass. It's a band pass. And this is in one dimension. This is in two dimensions. Okay. And this is the way to simulate this kind of thing. We see the edges, and the brain has to interpolate the box. Top of that, we are. Okay, so we have more green cones than red cones, and we have more red cones than blue cones. And now you can try to imagine why. Why do we have so few blue cones? Because we also have rods there. Part of the job is performed by the rods. Rods by 9, you also kind of see blue light. So we have blue cones and rods, so they compensate everything. Why do we have more green cones than red and blue? Why do you think we see better in the green? So our environment, we grew up in the savanna forest, we want to see very small details in the green. And then you are adapted to your environment. Okay, so this is the eye. Something else is the brain. So the brain has to do a lot of work. So it has to integrate in time for the fovea. It has to interpolate the colors in between. Then the visual system is located at the back of the brain. So the eye, so the information, the visual information is transmitted from the eye to the very back of the brain. And there are some people that work in this kind of stuff. They have divided the brain into different regions. So they call it V1, V2, V3. So the V1 is the low level operations. We have called it selective spatial temporal units. These are the ones that are integrated in time. And then we do this feature aggregation. So somehow we take the output of V1, put things together with construct features. And then there is another layer that pay attention to what is interesting in those features that we are seeing. And there's a hierarchy of processing at the low level things, and then features of higher level, higher level, until we understand what we see. And these makes a very nice connection. Have you heard of neural networks in deep learning, deep data? So anyway, all these artificial intelligences just about neural networks. So the structure of a neural network, they were originally designed to mimic our brain. So at a much lower complexity. So we have an input layer. This could be the layer coming from the eyes, and the hierarchy neurons that take the output, the response of these neurons, and integrate it with other neurons, and then these ones are spiking, and then they excite the next layer as well. So this resembles a bit like this structure V1 in this one that we have. And it has been shown by this. Only these ones. So you see this image. When you train a neural network, a computer one, when you look at what the first layers are doing, they're learning this kind of stuff. They're learning somehow edges, response to colors. So they are very, very low level responses. And then the next layer, they respond in this way. They are constructing pictures. So they're putting, okay, when you see two edges of this kind, one on the side of the other, then you have this feature. Then this feature is a feature. But you keep on constructing higher and higher level until there is a, for instance, when you see the picture of a dog, at the end, there is a group of neurons that are spiking, that are the ones that respond for dogs. And you have another one for cats, and another one for people, another one for your friends. You have a group of neurons that spike with responding to what you are seeing. But the first layers, they work like this.